Okay, this video is for AP Calculus, and we're talking about solving differential equations using a method called separation of variables. This is the main method that we use when we can't just do an antiderivative. So we've seen one method so far. Let's say that you have a first-order differential equation with just a first derivative, and when you solve for that first derivative, the right-hand side contains only the independent variable, the x variable. In that case, then solving this for y just simply means to undo the derivative. So we just take the antiderivative of the right-hand side, and therefore it's 1/6 x to the 6 plus the integration constant, and that is the general solution. Right? We could always double check that. If I were to take the derivative of this, it would be 6x to the 5th plus 0. And sure enough, that derivative would be this, so this is a solution to that differential equation. All right, but that works only if the right-hand side contains only the x variable, the independent variable. If you have a differential equation of this form, like let's say dy dx equals x times y, then we can't just take an integral of the right-hand side because we can't take an integral with a mixture of variables, at least not in the single variable course. So how do we do this? Well, we're going to end up taking two integrals, a separate integral on the left and the right. But first, we're going to separate the variables to put each side has only one of the two variables. So that's why this method is called separation of variables. First thing I'm going to do is I'm going to multiply this dx, whatever is in the bottom, to the other side. So if I multiply both sides by dx, I'm going to get dy is equal to x times y times dx, right? And that means that this side on the left is going to be the y side, and this side on the right is going to be the x side, because that's where the differentials are. The dy is on this side and the dx is on this side. But that means that this y is not on the correct side. Right, so what we're going to do is everything is multiplied here, so I'm going to divide both sides by y, and I get 1 over y dy equals x times dx. So at this point, we have now said that the variables are separated. So not all differential equations you can do this with, but in some cases where you have a right-hand side that's factorable into separate factors that are multiplied, you can just divide over the part that is the y and multiply over the dx, and you can separate the variables like this. Okay, to solve this, then what we're going to do is we're going to take an antiderivative of both sides. So on the left side, this is, let's see, the antiderivative of 1 over y is the natural log of the absolute value of y plus an integration constant. And over here, this is 1/2 x squared plus an integration constant. But what we tend to do is we just know that we're going to have two integration constants, so we combine them together into a single integration constant that we go ahead and put by default on the right side. So that c really is a combination of both c's moved together and lumped together. So this is the general form of the solution. Now, this is what we call, it's the general solution because we have not solved for c by giving an initial condition. And we also can say this is the implicit general solution because it's not yet solved explicitly for its dependent variable y. If we need to solve for y, which we should do unless the problem says not to, we're going to have to solve this resulting equation for y. So what I would do is to clear this y from inside the natural log, I'm going to say e to the left side equals e to the right side, because natural log and e are inverse functions, so they cancel each other's functions out. And that means I would have absolute value of y equals e raised to the 1/2 x squared plus c. Right? But whenever you have something like x squared, or x to the, let's say, 2 plus 3 power, you can split that into x squared times x cubed, right? Because that's how the exponent rules work. So that means this is equivalent to e to the 1/2 x squared times e to the c, right? And e to the c is itself a constant. So maybe I'll go back and call this constant 1. So I can now relabel this e to the c1 a new constant, which I'm just going to call c. So it's e to the 1/2 x squared times a constant c. And that means I can write this. The absolute value of y is equal to a constant times e to the 1/2 x squared. And because that constant could be positive or negative, that means that regardless of what's going on here, we could adjust with the constant, which means it's legal for me just to drop those bars here. So this is the general solution. Okay. Now, when you separate variables, sometimes the c is not just tacked on at the end. It is added at the end when we do the integration step, but when we solve this for the y variable, we get what's called the explicit general solution. That's this form here. And when we do that, sometimes the c ends up not just being plus c, it's buried in some way in here because it was part of the procedure that we used to solve for the y. So this is the correct form here, not e to the 1/2 x squared plus c, but c times e to the 1/2 x squared. All right, so this procedure is called separation of variables. And what you have to do is separate the variables to a y side and an x side. I always start by multiplying the x over so I can see this is the y side, this is the x side, and then get rid of anything that doesn't fit on the correct side before you take the antiderivative of both sides separately. So can you do this not all the time, but some differential equations, the right-hand side can be factored into two factors, a piece that contains the x and a piece that contains the y, which means that you're going to be able to divide this side over when you multiply the dx over. So, for example, this one here is not separable, right? When you have a y plus a sign of x, there's no way to factor this into a separate x and y, so there's no way to separate these. There's no way to move this y to this side without also moving the sign of x. And so that means this method will not work. And we don't have a method yet for solving this. We'd have to wait till next semester's course to solve that. We do learn methods then for solving this. But this one, although it looks more complicated, actually is separable because we've got a y squared here. We've got an e to the 3x plus 4y, which looks like it's mixed together, but that e to the 3x plus 4y can be separated into e to the 3x times e to the 4y, which means that we can bring the e to the 3x together and bring these two pieces together into the y factor. So just finishing the separation, but the next step would be 1 over y squared e to the 4y dy would equal e to the 3x dx. And in theory, you could integrate both sides here and find a solution, although I'm not sure that we have a solution for this using our integration techniques. Right. Anyway, this is what we call a separable differential equation because separation of variables method will work. We can separate the variables, and this is what we call a non-separable differential equation. Right. So just want to be clear that this will not work on all cases, but it will work on the cases that you encounter in this section. And then you also may be given an initial condition, and anytime you are given an initial condition like that, that means we want to solve for the c at the end of the problem. So let's go ahead and solve this problem, and you can go ahead and try this on your own if you like. But here's how I would do this. First of all, I'm just going to move this to the other side here by subtraction. So I have 2x y prime equals natural log of x. And then, let's see, this is really, this x prime can be written dy dx, natural log of x. Which means this x is, if I multiply by dx, I'm going to have 2x dy equals natural log of x dx. And definitely I have the y side and the x side here. This x is now on the wrong side, so I'm going to divide it over. I have 2 dy equals natural log of x divided by x dx. Okay. Now the 2, that can be on the left side, or we could move it over to the right side. If I move to the right side, it's going to become a fraction 1/2. So usually I leave it on the side, makes it not a fraction, but you could do it on either side. Okay, now that we have this, the next step would be to integrate. So let me show that step. An integral of 2 dy equals an integral of, I'm going to write that as 1 over x natural log of x dx. Right. The left side here is just 2y. But the right side, what is that? Well, I think we're going to have to do a u substitution. What if we did the u substitution where u was natural log? Because the derivative of natural log is 1 over x, and that means that 1 over x dx is du. So that means we could replace this with this natural log as a u, and this 1 over x times dx is the du. So now I have 2y equals 1/2 u squared plus c, and the u is natural log, so it's 1/2 natural log of x squared plus c. This is what we call the general, this is the implicit general form. Okay, and then the next thing we can do is, well, we've got to try to solve for the c. So I might change colors here. If x is 1 when y is 2, that means I should be able to plug in a 2 for this y, and a 1 in for that x. The natural log of 1 is 0, so that means that the c is 2 times 2, which is 4. And that means I can write this again, this right here, and fill in 4 for the c. So 2y equals 1/2 natural log of x squared plus 4. This is called the implicit particular form. It's particular because we have now used an initial condition to pick a specific particular c to fill in, to go through that initial condition. To make it the explicit form, we're simply going to solve for y, which means we will divide everything by 2. So y is 1/4 natural log of x quantity squared plus 2. This is the final solution, so that is in what we call the explicit particular form. Particular because it has no constants left, they've all been solved for, and explicit because it's been solved explicitly for the dependent variable y. All right, so that's a good example. We've got, let's see, two more examples here in this section. So for each of these, you could try pausing the video and unpause and see if you can solve. There's no initial condition here, so we will end up with a c, but we do want to solve for the y variable if possible. All right, what I would do first is multiply this dx to this side and multiply this y squared over here. I'll separate the variables. Y squared dy equals 3x squared dx. Might as well move the 3 over here. If I divided it over, it'd be 1/3. And we're going to take an antiderivative of both sides. On this side, this is 1/3 y cubed plus an integration constant that we'll add later. And then this is going to be 3x cubed over 3, right? Plus an integration constant. So that is 1/3 y cubed equals x cubed plus a c. Okay. Then what we could do is maybe triple everything to get rid of this 1/3. So that would be y cubed. I'm going to call this c1. So this is y cubed equals 3 times x cubed plus 3 times c1, which I'm just going to relabel that as a new constant, which I'm going to call c. So now I'm just going to rebrand this 3 times that constant, a new constant called c. And then finally I'm going to take the cube root of both sides. 3x cubed plus c. And that is the correct solution. Note that the c must be inside the cube root because you have to include it in the procedure that you're using. So when is the appropriate time to add the plus c? Right when you finish the last step of differentiation. You take the antiderivative, that's when you add the c, and then it stays in that location for the rest of the problem. Okay, so that's that one. That wasn't too bad. This one looks a little bit more complicated. Let's take a look. Again, you can pause the video and try it on your own first. All right, so let's see. Separating variables first. What if I did this? Square root of y prime equals negative square root of x. Square root of y dy dx equals negative square root of x. So the square root of y, which I'm going to write as y to the 1/2 dy, is equal to the negative square root of x, which is x to the 1/2 dx. So that is variable separated. Now we'll take an antiderivative. antiderivative of y to the 1/2 dy equals negative antiderivative. I'm just going to move the negative out right there. So the antiderivative here would be we would add 1 to get 3/2 and divide by 3/2. And then negative x to the 3/2 divided by 3/2 plus an integration constant right there. I'm going to leave that as a C1. Let's get rid of this by multiplying everything by 3/2. That would make this y to the 3/2 equals negative x to the 3/2 plus 3/2 times C1, which is a new constant. I'm just going to relabel that C. And then this would be a good time, I think, for us to plug this in. So let's go ahead. Usually before you solve for the y is the best time to plug it in while it's in implicit form. So for x, I'm going to plug in a 1, and for y, I'm going to plug in a 9. So this is 9 to the 3/2 equals negative 1 to the 3/2 plus c. So what is 9 to the 3/2 on the side here? 9 to the 3/2 can either be written as 9 to the 1/2 cubed, because that would multiply the 3/2, or it can be written as 9 cubed to the 1/2 power, right? But this is the same as the square root of 9 being cubed. And so that square root of 9 is 3. 3 cubed is 27. So this is just 27. And this is a negative, and then 1 to any power is 1. So if I add that over, that means c is 28. Yeah. Okay, so then I'm going to rewrite this. Go back to this version right here, and I've got y to the 3/2 power equals negative x to the 3/2 power plus the c of 28. This is the implicit form. And now we want to go ahead and undo this. So what I'm going to do is I'm going to raise the left side to the 2/3 power, because that will multiply to a 1 and give you just y. And this entire negative x to the 3/2 plus 28 will be raised to the 2/3 power. So that means y is negative x to the 3/2 plus 28 to the 2/3 power would be the result. Okay. Great. So usually I find that it's best to plug this in at this stage when we have the implicit form, because when you undo this, you end up adding complexity, and it's best to do that only in the last step if possible. All right, that should be it for that example. Hopefully that gives you enough to practice.